Now we're going to look at graphing piecewise functions. Here we have f of x equals 5x if x values are less than or equal to 0, and then we have 3 if x is greater than 0. So the first thing that I'm going to ask you to do when you're graphing a piecewise function is to look at what x values are mentioned in those restrictions. The x value that's mentioned specifically is 0. So we're going to draw a line at the x value of 0. Okay, so I'm going to look on my x-axis here, and I'm going to find where is x equal to 0, and I'm going to draw a line going up and down at that x value. This represents the cutoff for where each equation is going to be used. Okay, so 5x is used for x values that are less than or equal to 0. So on the left-hand side, I am going to put f of x is equal to 5x. So f of x will be using 5x for x values that are less than or equal to 0. Remember, less than means to the left. So when we talk about less, we mean to the left of that cutoff value of 0. It also says equal, so that means we can also use the actual line itself. Okay, we're going to use 3 if x is greater than 0. For x to be greater than 0, we have to be to the right. So on the right-hand side of 0, I'm going to write f of x is equal to 3. Okay, so these are the equations that are going to be used on either side of that cutoff x equals 0 line. Okay, to figure out what the graph looks like on either side of that cutoff line, we're going to make a table. So first I'm going to make a table. I'm going to choose x values, and we're going to plug them into the function, into that top equation, 5x. What x values am I allowed to choose? I'm allowed to choose any x values that are less than or equal to 0 to plug into that 5x equation. So when you are making your tables and you're choosing the x values that you want to plug in, if the restriction has an equal sign on it, I want you to include the number that's to the right of that equal sign. So I want you to include the 0 in your table for an x value. Okay, so I want you to include the cutoff value for x if you have that equal sign in part of your restriction. Okay, so since the equal sign is on the restriction for that top equation, I'm going to start with 0. Okay, I want you to include the restriction value. What other x values am I allowed to plug in? Well, anything less than 0. So that means anything to the left of 0 is also allowed to go in. So we have -1, -2, -3, and so on. Okay, so we're going to plug in a few of these values and then see what the graph looks like. So I'm just going to go ahead and just mark all the way to -10 to fill up my graph. Okay, so let's see what we get. So we can plug in an x value of 0. So that's 5 times x, so that's 5 times 0. So that gives me 0. Now what that means is that I can plot the point 0, 0 on my graph. So we're going to also show what ordered pairs we're now allowed to plot. Okay, I'm going to draw the graph here in green. So I have 0, 0. So I'm allowed to plot that point on the actual line. Okay, because x equals 0 is included. So I got 0, 0, closed filled in circle at that point that I plotted. Okay, so let's plug in a -1. So that's 5 times an x value of -1, and that gives us -5. So the point that I'm going to plot is -1, -5. So -1, -5 is here. So I'm going to plot that point. I'm going to go ahead and just label it so you can see what I just plotted. So far we have this line. Okay, what happens when I plug in a -2? 5 times -2 is -10, so I can plot the point -2, -10. I'm going to plot that in green so we can see that graph. So -2, so -1 was here, -2 is here, -2, -10. We're going to plot that point there. Okay, so let's plug in a -3. So we have 5 times -3, and that's equal to a -15. So negative 3 comma negative 15 is the point that I would plot. Now when I come over to my graph to actually plot that point, I see that I don't have enough graph to actually plot negative 3 comma negative 15. The y values on my graph stop at negative 10, and so I can't actually, I would have to go below my screen to actually graph that point. So instead of plotting that point, what we're going to do is we're going to say continue forever in this direction. So I'm going to attach an arrow there to say I would keep going and plotting more points if I could, but I have fallen off my graph and I can't plot any more points. So I'm not going to plot these. I could if I wanted to. If I had a big enough piece of graph paper, I could plot all of these points. But since I can't plot all of those points, then I'm just going to put an arrow to say keep going forever in that negative direction for those x values and in that negative direction for those y values that I would plot if I could. Okay. Now, before we move on, I want to make note of something. When we plugged in that x value of 0, and we got that 0.00, we put a closed filled-in circle there, right? Let's just make a little note there. We used a closed circle. Okay, why were we allowed to put a closed circle? Because when we look at that first equation, the x value of 0 was included. So since it was included for that graph, we put in a closed circle. Okay, so what we're about to do for the next equation is going to be a little bit counterintuitive at first. Okay, so we're going to make a table again. We're going to plug in some x values into that second equation, which is just 3, which is nice. Okay, but what I want you to do, and this might be uncomfortable at first, but what I want you to do is I want you to include the cutoff point of 0 here as well. You say, but Miss Spalding, 0 is not included for that second equation, so why are you doing that? Okay, here's what I want you to do for that one. When you plot that point, I want you to put an open circle. Okay, because 0 is not included for that second equation, but I want you to put an open circle to make note of that. Okay, we want to go right up to that line and plot whatever we can on that line, but for this equation, since 0 is not included, we're going to put an open circle when we plot that point. Okay, what other x values can we include? Well, we want x values that are greater than 0, so I can include 1, 2, 3, 4, and so on. Anything that's larger than 0 can be included. Now everything after this is going to be a closed, filled-in circle that we plot on the graph, because all of these are included. Okay, so they're all part of that inequality. So for anything else we plot after that 0, everything else is going to be closed, filled-in circle. Now the nice thing about this equation, when we plug in any x value, the answer is always exactly 3. Okay, so in order for us to plug an x value into that equation, we would have to see an x, right, on the right-hand side of that equal sign, and then we put parentheses, and then we drop that x value into the parentheses. But in this equation, there is no x. There's nothing to replace with parentheses. The answer is just 3. That actually makes all of these calculations very easy. All of our answers are just 3. Okay, so the points that we end up plotting, 0, 3, 1, 3, 2, 3, and so on. Okay, we're going to plot as many of these as we can. We're going to fill up our piece of graph paper. Okay, we actually could go a little more, right? We could do 7, we could do 8, we could do 9, we could go all the way to an x value of 10 for my graph purposes, right? If you want to go 11 and 12, you can. The only restriction here is that x has to be greater than 0. But all we want to do is we want to make sure we fill up our piece of graph paper, and once we fall off, we'll put an arrow to indicate that you could keep going if you wanted to, but we're going to stop. Okay, so you could keep going, 13, so on. Okay, but we're just going to fill up our piece of graph paper and then stop and put an arrow. So these are all the points that we're technically allowed to plot for that second equation. Okay, so I'm going to break out my green pen again, and we're going to start to plot some points. Now remember that we said the first point here was actually an open circle because 0 was actually not included for that second equation. Since it's not included, I still want to plot x equals 0, but I'm going to plot it as an open circle. So 0, 3, that's right here. So I'm going to put an open circle at 0, 3. Okay, we're going to make a note of that. There is an open circle there. Remember, officially 0 is not included, but we want to go as close as possible to that line as we can. So we want to know what point we would plot if we could. We're going to plot it as an open circle. Okay, remember everything else after that is going to be a closed circle. Alright, so now the next point is 1, 3. There's 1, 3. That open circle was 0, 3. We'll make note of that. The next point is 2, 3. 3, 3. 4, 3. So you start to see a little bit of a trend here, right? All of these points that we're plotting from here on out are all at that same exact y level. 10, 3. 11, 3. Now, I could keep going 12, 3, 13, 3, but I fall off my graph. So I'm going to connect all of those dots right up into that open circle. I'm going to connect all of those dots. And then I'm going to put an arrow to say, I would keep going if I could, but I have fallen off my piece of graph paper and I can't plot any more of those points. So we're going to put an arrow on there to say that the graph continues in that same pattern forever to the right. Alright, so everything we see there in green is our piecewise function that has been graphed. Okay, so the takeaway here is we're going to make tables for each equation. In both tables, we're going to include that cutoff value, that number that's mentioned in both restrictions. In one of the tables, the x value, that cutoff x value will be included, so we'll plot that as a closed filled-in circle. In the other table, that x value, that cutoff x value, will not be included, so we will plot that, but we will plot it as an open circle. Okay, so each of the equations should have some sort of point plotted on the line, maybe as a closed circle and maybe as an open circle. When you fall off the graph, we're going to put arrows to indicate that you could keep going forever in those directions off of your graph and plotting points if you could. The last thing that I want to mention before we do another example is that this is supposed to be a function, right? So what do we know about functions? They're supposed to pass the vertical line test. So when we graph this function, when I look at everything there in green, if I take a vertical line, the vertical line should only cross this graph one time. So every place that I can draw a vertical line, the vertical line should only cross through the graph one time. So you'll notice that when I get to that cutoff x value of 0, right, we kind of look like there's 2 points plotted there, but remember, this one is a closed filled-in circle. That's included. This is an open circle. So we don't actually violate the vertical line test because I'm only crossing through officially one point, and that's that point 0, 0 here. There is not actually a point at 0, 3. That's an open circle not included. So as I move from left to right and I'm looking at my vertical line test, this graph is a function because it passes the vertical line test. All of our piecewise functions should pass the vertical line test. How would it fail the vertical line test? Well, if I had accidentally filled in this circle. If I fill in this circle, and I'm not supposed to, but if I did fill it in, I should see a problem. Because when I get to here, I actually do cross through both 0, 3 and 0, 0. I cross through 2 points at the same time with that vertical line. Then it would fail the vertical line test, and then f would not be a function. Okay, so at the end, if you want to test yourself out, you could say, does it pass the vertical line test? And you know that if it doesn't pass the vertical line test, then you did not graph the piecewise function correctly. In your notes, I have included 6 steps for graphing piecewise functions. These are the 6 steps that we used to graph the previous piecewise function, and I'm going to apply those 6 steps to the next piecewise function as well. We are asked to graph the piecewise function. We have f of x equals x plus 5 if x is less than 3. We have x minus 5 if x is greater than or equal to 3. So the first thing I'm going to do is I'm going to look into those inequality restrictions on x, and I'm going to draw a line, a vertical line, at the x value that's mentioned in those restrictions. So the specific number that's mentioned is a positive 3. So I'm going to find a positive 3 for x, which is right here, and I'm going to draw a vertical line This represents what we call the cutoff x value. Now we want to decide which equation will be plotted to the left of that line and which equation will be plotted to the right of that line. So the top equation, x plus 5, is only for x values that are less than 3. So not equal to 3, but strictly less than. Okay, when we say less than, we mean to the left. So we're going to graph the equation f of x equals x plus 5 to the left of that red line. Okay, so the bottom equation is going to be graphed where x values are greater than or equal to 3. Greater than means we're going to plot to the right. Now it can also be equal to 3, so it can also be plotted on that line. So to the right and on that line, we're going to graph f of x equals x minus 5. All right, so now we're going to make some tables. Okay, I'm going to start with the top equation. We're going to plug in some x values and we're going to plug them into this top equation. Okay, then we're going to find some points and we're going to plot them on our graph. Okay, so what x value am I going to start with? Well, I'm going to start with an x value of 3. Remember that 3 is that cutoff x value. We're going to include it in both tables. But since 3 is not officially included in that top equation, we're going to put an open circle. So when we plot this point, we're going to plot it as an open circle. All right, what other x values can we include? Well, everything to the left of this line, we want to include those x values. So we can include 2, 1, 0, and go all the way to negative 10. So negative 1, negative 2. Officially, I can go all the way to negative infinity, but I will fall off my graph if I do that because my x values only go to negative 10. So I'm just going to put everything in there from x values from 3 all the way to negative 10, and we'll see what we get. Okay, so let's see what we get. So I'm going to plug in a 3 in place of x. So that's 3 plus 5, and we get out an 8. So a 3 goes in, a y value of 8 comes out. So remember, I'm going to plot that point as an open circle. Okay, so here's our x value of 3 and our y value of 8. Just label a little bit right here. So I'm going to put an open circle there, and I'm going to label that as 3, 8. Okay, so what is our next point going to give us? Remember, everything else after this is going to give us a closed filled-in circle. So we plug in an x value of 2, that's 2 plus 5, that gives us out a y value of 7. So I can plot the point 2, 7. So here's my x value of 2, and here's my y value of 7. Okay, everything else is going to be a closed filled-in circle. Okay, we're going to do now 1 plus 5. That gives me 6. So I get 1, 6. Now let's just do a couple of these. We're going to plug in an x value of 0. We get 0 plus 5, which is 5. So 0, 5. Okay, now I'm going to plug in an x value of negative 1. We're going to add 5, so I get a positive 4. So that's negative 1, 4. Okay, I plug in an x value of negative 2. So that's negative 2 plus 5, which gives me a positive 3. So negative 2 goes in, y value of positive 3 comes out. Okay, plug in an x value of negative 3. Negative 3 plus 5 gives me a positive 2. So I get negative 3, positive 2. All right, let's plot those and see how far we get on our graph. So what do we have? 1, 6. There's an x value of 1. Here's a y value of 6. So there's 1, 6. 0, 5. X value of 0 here, y value of 5 here. So far I have a line that connects the open circle to these 3 closed circles. Okay, negative 1, 4. So an x value of negative 1 and a y value of 4. That would put me at a point right there. Negative 2, 3. Here's an x value of negative 2 and a y value of 3. So that puts a closed filled-in circle there. Okay, here's an x value of negative 3 and a y value of 2. So that puts a closed filled-in circle there. Okay, keep going, plotting points until you fall off your piece of graph paper. So negative 4 comma 5, I get a positive 1. That's negative 4 comma 1. Negative 5 plus 5, I get 0. So that's negative 5, 0. X value of negative 6, we're going to add 5 to that. I get a negative 1. So that's negative 6 comma negative 1. Okay, let's plot those. See how far we get. Okay, so we need negative 4, y value of positive 1, I'll go here. Negative 5 comma 0, that's here. Negative 6 comma negative 1. So now I'm going below the x-axis, getting into those negative values. So negative 6 for x, negative 1 for y is here. Do you see a pattern here? So it looks like we're going to the left one and down one every single time. That pattern actually should continue as we start to find more points. Let's just prove that to ourselves. Since I can keep going forever, we'll go ahead and put our arrow because we've fallen off the graph. Okay, so if you see a pattern, you can use that pattern to keep going. I'm going to prove that that pattern really does work. Negative 7 plus 5, that will give me a negative 2, so that's negative 7 comma negative 2. And that's what I have here, right? Negative 7 comma negative 2, there's that point right there. Okay, negative 8 plus 5, that would give us a negative 3. So that's negative 8 comma negative 3. That would be right here. So we got that point, which is good. Negative 9 plus 5, we get a negative 4. So that's negative 9 comma negative 4. So that would be right here. And then a negative 10 plus 5 will give us a negative 5. So negative 10 comma negative 5. Okay, that would be right here. Now officially, since this x value is just less than 3, I could choose negative 11, negative 12, negative 13, and so on. But plugging those points in will give us points that just fall off our graph. So since our graph extends beyond the piece of graph paper that I see, I'm going to put an arrow to say I would keep going to the left if I could. But since I can't plot any more points on the graph, I'm just going to put an arrow there. Okay. All right, what about the right side of the graph? We're going to make a table for that as well. Okay, we're going to choose some x values and we're going to plug them into that second equation, x minus 5. Okay, what x value am I going to put in? So remember, we always want to include the cutoff x value. So I'm always going to include, in this case, that cutoff x value is 3. So I'm always going to include that cutoff x value. Now, the 3 in that second equation is included because of that line. So we're going to use a closed circle when we plot this point. Okay, so when I plug in a 3, that's 3 minus 5. I'm going to get negative 2. So we're going to plot the point 3 comma negative 2. Okay, that's going to be a closed filled-in circle. 3 comma negative 2, that's down here. Okay. What other x values could we plug in? We could plug in anything that's larger or to the right of 3, right? Because that's x values greater than or equal to 3. We already did the or equal to 3 part. Now we're just looking for values that are greater than 3. So we're looking for any of these x values to the right of that line. So we're going to use 4, 5, 6, 7, 8, 9, and 10, and we could keep going until we fall off our graph. Okay, so let's find some of these. So that's an x value of 4, that would be 4 minus 5, that gives me a negative 1. So 4 comma negative 1. X value of 5, that's 5 minus 5, I get 0. So we're going to plot 5 comma 0. X value of 6, that's 6 minus 5, that gives me a positive 1. So I get 6 comma 1. So let's plot those points and see how far we get. Alright, so 4 comma negative 1 would be here. 5 comma 0 would be here. 6 comma 1 would be here. And I think we start to see again to the right of that line we're seeing a pattern. It looks like I go to the right one and up one to get to the next point. Okay, if you notice a pattern, you can use that. So all of these points get connected. And since I can use x values that are larger than 10, I'm going to put an arrow to say that I could keep going to the right forever, choosing x values that are larger than 10. But since I fall off my graph, I'm just going to indicate that I could keep going with an arrow. Okay, if you plug these points in, you get 7 minus 5, which gives you a positive 2. So you should plot the point 7, 2. So that would be here. We already have that one from the pattern. 8 minus 5 will give us 3. So that's 8, 3, which is right here. We got that from our pattern. Plugging in x value of 9, I get 9 minus 5, which is 4. So that's 9, 4. That's there from our pattern. Plugging in x value of 10, we get 10 minus 5, which gives us a positive 5. So 10, 5, which is here. Alright, if you plug it in 11, you would get a 6, and so on. So I'm going to stop there. And everything that we have here in green, so all of those green filled in circles, everything we have in green to the right and to the left of that red vertical cutoff line is part of our piecewise function graph. Okay, does it pass the vertical line test? Okay, so there's my vertical line. And I'm just going to move along the graph to the left and to the right. So make sure that vertical line only touches the graph at one point every time. So here it only touches the graph in one point, because here I'm not including that open circle, so there's not a point there, but there is a point here. So we have not violated the vertical line test. Everything that we see there in green is representing a function. We are asked to graph the piecewise function. We have f of x equals 6 if x is less than or equal to negative 2. And we have negative 6 if x is greater than negative 2. So the first thing that we're going to do is we're going to look at those inequality restrictions, and we're going to determine what is the cutoff x value. So what's the number that's mentioned next to the inequalities, next to x in those inequality restrictions? The number that's mentioned is negative 2. So I'm going to find negative 2 as an x value on my x-axis. I'm going to draw a vertical line that goes all the way up and all the way down from there. Okay, so this x equals negative 2 is what we call that cutoff x value for those piecewise functions. Now we're going to decide which equation goes to the left of that line and which equation goes to the right. Okay, so the top equation is just 6 when x is less than or equal to negative 2. So less than means left. So to the left, we're going to graph f of x equals 6. Okay, the bottom equation is good when x is greater than negative 2. Greater than means to the right. So on the right side, we're going to graph f of x equals negative 6. Okay, now we're going to make some tables. Okay, I'm going to start with the equation on the left. So f of x equals 6. We're going to start with the cutoff x value of negative 2. Okay, and then we're going to include all the x values that are to the left of negative 2. So that would be negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, negative 10. Now officially we could keep going to everything that's left of negative 2, but since my graph stops at an x value of negative 10, we can officially just stop there and put an arrow if we keep going. Is the negative 2 included or not included for that top equation? And it is included. So since it's included, we're going to put a closed circle when we plot this point. Now what's really nice about this piecewise function is that there are no x values to plug in. When we plug in the x values, we just get one answer. That's called a constant. We just get 6. Okay. So this is really nice. We're going to get 6 all the way down for all of these values. Okay, now we're going to plot all of these points. Okay, so -2, comma, y value of 6. We're going to plot that as a closed filled-in circle, okay, on that line. And then -3, comma 6. So you notice the y value is the same for all of them. -4, comma 6, -5, comma 6. So we're getting this horizontal line. So all these closed filled-in circles are getting plotted at the same y value level of 6. Now remember, we could keep going, so I'm going to connect all of those closed filled-in circles, and then I'm going to put an arrow to indicate that the graph could keep going to the left forever, but I'm just going to indicate that with an arrow. Okay, now let's do the equation on the right side. Plug in our x values, and then the function we're going to graph is f of x equals -6. So what x values am I going to plug in? We're always going to include that cutoff x value, but it's not officially included, right? Because we don't have the equals to for that bottom equation. So when we graph this, we're going to put an open circle, since that x value of -2 is officially not included on that graph. Okay, what other x values are we going to put in? Well, anything to the right of that line. So all of the x values to the right of that vertical line. So -1, 0, 1, 2, 3, 4, and so on, right? Until we fall off the graph. So I'm just going to go all the way to 10. It could keep going if we wanted, for all x values that are greater than -2, but we would fall off our graph if we kept going. Okay, so what are all of the answers going to be? There's nothing to plug in for x, right? Because it's just -6. So all of the answers are just that constant -6. That makes this really easy. All the way down, we're just going to plug in some -6s. Okay, we could keep doing forever again. Now remember that for that first point, we're plotting an open circle. So -2, comma -6, that's down here. We're plotting that as an open circle. Okay, we want to make sure that we don't violate that vertical line test. -1, comma -6, it's here. 0, comma -6. So we see all of the y values are -6, so we're just going to plot all of these closed filled-in circles basically along the same horizontal line, where y has the same value all the way across of -6. Okay, so I'm going to connect the open circle and all of the closed filled-in circles. Then we're going to put an arrow going to the right, since we could go to the right forever. Okay, now I'll let you use the vertical line test just to prove to yourself there that what we have there in green, definitely all together, that entire graph represents a function. Graph the piecewise function. We have g of x equals 0 when x is less than -3. We have -2x when and if the x value is between -3 and 0. So the x value has to be greater than -3 or equal to -3, but less than 0. Okay. We have x squared when x values are greater than or equal to 0. So this one is a little different because we actually have 3 different equations. A piecewise function can actually have as many functions or as many equations. A piecewise function can have as many equations as you wish. When we look in the restrictions, we actually see 2 different x values that are included, 2 different numbers that are included in all of those inequality restrictions. I see -3, so I'm going to draw a vertical line starting at -3 on that x-axis. So there's one of the cutoff x values. But we also see that 0 is mentioned. So 0 is another cutoff x value. Okay, we're going to draw a vertical line for every number that we see included in those inequality restrictions. So we actually have 2 cutoff values. Alright, now we need to decide which equations are used where. Our top equation, 0, is good for x values that are less than -3. Remember, less than means left of. So left of -3. So left of that vertical line for x equals -3 cutoff x value. So we're going to graph g of x equals the equation 0 to the left of -3. Okay, what about in between -3 and 0? We're going to graph -2x. So in between, we're going to graph g of x equals -2x. So that equation is going to go in between those two lines. Okay, x squared, that's going to be graphed to the right of x equals 0 because x is greater than or equal to 0. So to the right, we're going to graph g of x equals x squared. Okay, because we're talking about greater than 0, which means to the right of 0. Okay, so let's start making some tables. We'll start on the left for g of x equals 0. Plug in some x values. See what we get. Okay, so what x values are we going to plug in? We're going to start with the cutoff value for that equation. So I'm going to start with -3. Is that going to be included or not included? Well, I don't see a line, so that's going to be not included on this graph, which means we're going to use an open circle when we graph this point. Okay, what other x values can we use? Well, we can use anything to the left of -3. So -4, -5, -6, -7, -8. Keep going, and we go all the way until I get to -10. Even though we know officially we could keep going, plotting -11, -12, but then we know we're going to fall off our graph. Okay, what are all the y values for each of these? Well, they're all 0. There's no x value in that equation. So since there's no x variable in that equation, there's nothing to plug in. Our answer is just always constantly 0. Okay, so let's plot these points. -3 for x, a y value of 0 is right here. Right? And we're plotting that as an open circle since it's not included. -4, 0. It's right there on the x-axis, right? Because the y value of 0 is right here. So we have an open circle there, closed circle for the rest of the points. -5, 0. So all of these points get plotted right there on top of the x-axis where the y value is 0. So we're going to connect that open circle to all those closed filled-in circles, and then we're going to put an arrow to indicate that we could keep choosing more x values to the left of -10, but we're going to put an arrow there to indicate that instead of plotting all of those points forever. Okay, what about the middle graph? Okay, we're going to plug in x values, and we're going to plug them into the equation g of x equals -2x. We're going to plug in the restrictions, those values that are mentioned in the restrictions, those cutoff x values. So we're going to plug in -3, and we're also going to plug in everything in between -3 and 0. Okay, so that means -2, -1, and then we're also going to include 0. Now, is -3 included for that equation? Yes, it is. It's included, so I'm going to use a closed circle for -3. Okay, so for each of those cutoff x values that you include in the table, you want to make sure that you indicate whether it's a closed circle or an open circle. Is 0 included? I do not see a line, right, underneath that inequality symbol next to 0 and x. So 0 is not included, so I'm going to put an open circle when I plot the point for 0. Now this time I do have an x value to plug in, because it's -2 times x. So for each of these, we're going to do -2 times parentheses. And we're going to plug in an x value of -3, -2, -1, and then 0. Okay, let's see what we get. -2 times -3 is a positive 6. So we're going to plot the point -3, 6. -2 times -2 gives me a positive 4. So we're going to plot the point -2, 4. -2, -1 is a positive 2. So we're going to plot the point -1 for x and a y value of 2. And then negative 2 times 0 is 0. So we're going to plot the point 0, 0. I'm going to go back to my green marker to graph the function. So negative 3 for x and a y value of positive 6 is up here. That's a closed filled-in circle. Remember, we're deciding that because in the restrictions, there's a line underneath that inequality symbol between x and that negative 3 cutoff x value. So included, closed filled-in circle. Okay, the rest of them are going to be closed filled-in circles until we get to 0. So negative 2, 4, that's here, closed filled-in circle for everything in between. Negative 1, 2, that's here. Okay, but when I get to the plotting the point 0, 0, I have to put an open circle. So I'm going to put a big open circle there at the origin. We're going to connect all of those points. The open circle and the closed circle all get connected. Okay, so that is the graph of negative 2x in between negative 3 and 0. Okay, so we have one more, right? We need to know what's happening to the right of x equals 0. So we need to graph x squared. I'm going to make the table over here. So we're going to choose some values for x, and we're going to plug them into g of x equals x squared. Okay, what x values am I going to plug in? Well, let's look at that equation. What cutoff x values are included in that inequality next to that equation? Well, I see a 0, so I'm going to include 0. Is 0 actually officially included? Yes, it is, because I see that equal sign. So since it's included, I'm going to put a closed filled-in circle. So when I plot that point, we're going to put a closed circle. Okay, so what other x values can I include? Well, anything that is larger than 0, right? So it's everything to the right of 0 on my number line. So we can plug in a 1, 2, 3, 4, 5, 6, all the way until we fall off our graph at an x value of 10. Alright, so let's plug these points in. We can put parentheses everywhere we have an x, so it's basically parentheses squared for each of these x values. Parentheses squared. Okay, let's see what we get. I'm going to plug in a 0. 0 squared is 0. So I get the point 0, 0 to plot. Okay, the next point is 1 squared. Well, 1 squared is 1, so x is 1, y is 1. So I get to plot the point 1, 1. Okay, we'll plug in a 2. 2 squared gives me 4. So x is 2, y is 4. Plug in a 3 in the parentheses. 3 squared gives me 9. So I get to plug the point in. So I get to plot the point 3, 9. Okay, we plug in a 4. 4 squared is 16. So I get to plot the point 4, 16. Now our y values stop at 10, so I'm going to stop there. All of these points that I would continue to find would have y values that are much larger than I could plot on my graph. Okay, so I'm going to plot these points that I can, and we'll go from there. I'm going to go back to my green marker. I'm going to plot the point 0, 0. Okay, now I want you to see something. This is pretty interesting. This is a little different. I want you to see something. This can happen sometimes. When I plot the point 0, 0, it's going to go inside of this open circle. So it's actually going to fill in the open circle that middle equation or that middle graph left open. That is okay. There was no point there. Remember, it was left empty. One of the other equations can fill in empty circles of the other. That is perfectly fine. So now it just looks like a big closed filled-in circle. Okay, that is okay. Sometimes that happens, and that is perfectly allowed as long as you don't plot 2 points on the same vertical line. Okay, we did not plot one point on top of the other. One left an open circle, so one left it empty, which left it open for another equation in the piecewise function to fill in that open circle. That is completely perfectly fine. And in fact, when you look at this, you see no evidence of an open circle at all. Once again, that is completely fine. Okay, so we got that closed filled-in circle at 0, 0 plotted. The next point is 1, 1. That's here. 2, 4. that's here. 3, 9, okay, that's here. And then 4, 16 we said was way up here somewhere, falls off my graph. Now, do you recognize this shape, right? Isn't that my square function? That's that U-shaped graph. What we actually end up plotting is the right side of that U-shaped graph only. So when I connect these points, I'm connecting them with that kind of that curvy right side of that U-shaped graph. Then I'm going to put an arrow to indicate that I could keep going, plugging in larger and larger x values. But since I fall off my graph, I'm just going to put an arrow to indicate that we could keep going if we wanted, but we're going to stop at the end of our piece of graph paper. Okay, does this represent a function? Okay, let's take our vertical line test and let's use it. So make sure that every vertical line that you could possibly imagine drawing only crosses through the graph one time. So when we get to here, we have a closed filled-in circle. Here we have an open circle. So there's only one point that the vertical line is actually touching, and it's this point here. Okay, keep going, passes the vertical line test. Remember, here we only have one point plotted, so that's fine. Okay, keep going, good to go. All of these pieces pass the vertical line test, and the entire graph altogether passes the vertical line test, so the entire graph represents a function.